Good morning. Now we'll find out how to find the Ctft of a double-sided real exponential signal given by e raised to minus a mod of t. We know how to implement the signal when the modulus of t function is given. Modulus of t has got the value minus t when t is less than 0, and it has got the value t when t is greater than 0. Substituting those two conditions and substituting for t is equal to 0, we can split the function as e raised to minus at for t greater than 0. When t is equal to 0, this is of the form e raised to 0, which will give the value 1. And for t less than 0, it is of the form e raised to minus a into minus t, which is equal to e raised to at for t less than 0. Hence we can split the integral into two sections, that is minus infinity to 0 and 0 to infinity. For minus infinity to 0, that is for t less than 0, we have e raised to at here, x of t's value, and multiplied by e raised to minus j omega t d omega. That is your standard equation. Plus 0 to infinity, that is for t greater than 0, we have got the value e raised to minus at into e raised to minus j omega t dt. And next we'll integrate it. Before integrating, we'll just combine these terms of exponential, that is e raised to a minus j omega t dt, and here if you're taking the negative sign outside, we'll get it of the form e raised to minus a plus j omega t dt. On integrating, we'll get it of the form e raised to a minus j omega t by a minus j omega with the limits minus infinity to 0, and here on taking the negative sign outside and integrating it, you will get it of the form e raised to minus of a plus j omega t by minus of a plus j omega of the limits 0 to infinity. And the next step, we'll give the limits, that is we'll take this 1 by a minus j omega outside, e raised to 0, and for next lower limit is e raised to minus infinity, and here we'll take minus 1 by a plus j omega outside, and we'll give the limits e raised to minus infinity minus e raised to 0. You know the value of e raised to 0 is 1 and e raised to minus infinity is 0. On substituting that, we'll get of the form 1 by a minus j omega into 1 minus 0 minus 1 by a plus j omega into e raised to minus infinity has got value 0 minus e raised to 0 has got value 1. And in the next step, we will have 1 by a minus j omega into 1, that is 1 by a minus j omega. Here this minus 1 into minus 1 will become plus 1, hence 1 by a plus j omega. Denominator is of the form a minus b into a plus b. We'll cross multiply it. On cross multiplying this section, we'll get a plus j omega. On cross multiplying like this, we'll get a minus j omega. Denominator part it is a square minus b square, which is equal to a square plus omega square. This j omega and j omega gets cancelled, which will give you 2a by a square plus omega square. Hence, we can summarize that e raised to minus a modulus of t has got the Ctft of the form 2a by a square plus omega square. This is again another general form of Ctft. And again we are plotting the magnitude and phase spectrum. Here also magnitude spectrum is computed by using the formula root of a square plus b square, where a is the real part and b is the imaginary part. Here we don't have the imaginary part, we have only the real part. So mod x of omega will give you the value 2a by a square plus omega square for all omega. And for omega is equal to 0, if you are giving, you will get it of the form. For omega is equal to 0, if you are plotting, we will get 2a by a square, which is equal to 2 by a, which is plotted over here. And for all the other sections, it is decreasing. And here angle of x of omega is nothing but tan inverse of b by a. We have got the b part, that is the imaginary part, is equal to 0. Hence tan inverse of 0 is equal to 0. Hence phase spectrum has no value, that is tan inverse of b by a is tan inverse of 0 by the a part, that is the 2a by a square plus omega square, which is equal to 0. Hence angle of x of omega has got the value is equal to 0. So that's all about the function, that is double-sided real exponential signal e raised to minus a mod of t. In the next section, we will find the Fourier transform of x of t is equal to 1. X of t is equal to 1 is a special case which do not satisfy the Dirichlet's condition, that is If you are seeing for the Dirichlet's condition of Ctft, you can find that integral over minus infinity to plus infinity mod x of t dt, if it tends to infinity, then the Dirichlet's condition is not being satisfied. So in this case, we use the duality property of Ctft, which was already dealt in the previous class. You can refer to it in the table of properties of Ctft. The duality property states that if x of t Fourier transform gives you capital X of omega, then capital X of t Fourier transform should give you 2 pi into small x of minus omega. That is your duality property. So in this case, our x of t is equal to delta of t, that is 1. X of t, we are considering it as delta of t, and delta of t Fourier transform will give you delta of omega, and delta of omega or x of omega. X of omega of delta of t is nothing but 1. We have already found out. That is the Fourier transform of delta of t is 1. So x of omega is 1. That is delta of omega is 1. So you have to use the second section of the duality property. That is x of omega is equal to 1. Here x means delta. Hence delta of omega is equal to 1. Hence delta of t will be also equal to 1. Because this is not a function of omega. It is not a function of omega, it is just a constant. So if x of omega is equal to 1, then actually x of t will be also equal to 1, capital X of t. This section, this is also equal to 1. Hence x of t Fourier transform will give you 2 pi into x of minus omega. We know x of t is equal to 1. Fourier transform will give you 2 pi into delta of minus omega. Delta function is an even function of omega, hence we can write delta of minus omega. Here this delta of minus omega is delta of omega. Even function, we know what is even function. X of minus t will be equal to x of t. So delta of minus omega is equal to delta of omega. On substituting that, we will get the Fourier transform of 1 is nothing but 2 pi into delta of omega. That is how you find the Fourier transform of constant 1. That is 2 pi into delta of omega. And in the next section, we can see how we have generalized it. Here it is 1. Instead of 1, even if it is any of the constant, let it be a, we can find out the Fourier transform by using the formula 2 pi into a into delta of omega. For example, if a is equal to some half, then it will have the form 2 pi into half into delta of omega. Okay, 2 and 2 will get cancelled and it will be pi into delta of omega. Like that you can find for any of the constant values. That is for the Fourier transform of 1. In next section, we will deal with the Fourier transform of cos omega naught t. We use the Euler's function and we split cos omega naught t as e raised to j omega naught t plus e raised to minus j omega naught t by 2, which is again split as half is splitted among both the signals. Half e raised to j omega naught t plus half e raised to minus j omega naught t. Mark it as equation number A. We have already just now dealt that the Fourier transform of a constant, that is a, is given by 2 pi a of delta of omega. Hence Fourier transform of half will be 2 pi into a's value is half delta of omega. That is the 2 and 2 gets cancelled and we will get the Fourier transform of half as pi into delta of omega. Okay, so this is your first equation. And next, by frequency shifting property, we have e raised to j beta of t x of t. Fourier transform will give you x of omega minus beta. This was also being given in the table of the properties for Ctft. Please refer to that. You will have a frequency shifting property like this. So here you have e raised to j omega naught t as well as e raised to minus j omega naught t. In this formula, we have e raised to j omega naught t as well as e raised to minus j omega naught t. So on substituting for beta equal to omega naught, we will get the Fourier transform as x of omega minus omega naught. Here beta has got the value omega naught. This is your general form. This is what is there in our equation. E raised to j omega naught t. Omega naught is equal to beta. Then instead of beta, we will get x of omega minus omega naught. In the same way, e raised to minus j omega naught t means beta. You will substitute minus omega naught. Then you will get x of omega plus omega naught. Hence on substituting this 1, 2 and 3, these three equations, in equation number A, we will get it of the form half into e raised to j omega naught t plus half into e raised to minus j omega naught t as pi into delta of omega minus omega naught plus pi into delta of omega plus omega naught. How this happens is that x of omega is pi into delta of omega, and finally you have to frequency shift the signal x of omega, which will yield you omega minus omega naught. So instead of omega here, you have to, in the first section you have to put omega minus omega naught, and the second section you have to put delta of omega plus omega naught. Hence you can say that the Ctft of cos omega naught is, you can take the pi outside, delta of omega minus omega naught plus delta of omega plus omega naught, and you can plot it also here, that is omega minus omega naught. Here also you have got impulse, here also you have got an impulse. This is impulse shifted by an amount of plus and minus omega naught with an amplitude of pi. That is what is being mentioned here, and here the phase spectrum comes like this. Okay, hope it's clear. In the same way we can prove for sin omega naught also. In the next section we have the Fourier transform of the signum function. Signum function is nothing but it has got the value of plus 1 for t greater than 0 and minus 1 for t less than 0. So this can be depicted as 2 into u of t minus 1. It is a general form. Just imagine u of t. U of t has got the value 1 for 0 to infinity, and signum function has got the value of 1 from 0 to infinity too. So if it is 2 into u of t, then it will be 2 here. Then 2 into u of t minus 1 means it will be 2 minus 1, that is 1 for t greater than 0, and for u of t it has got the value of 0 for t less than 0. So in this section it will be 0. So 0 minus 1 will give you minus 1. So that is how you can represent signum of t. Signum of t can be represented as 2 into u of t minus 1. Okay, so this is your first equation. And in order to find the Fourier transform, here we will just differentiate both the sides, d by dt of x of t, and on differentiating this u of t, you get it as 2 into delta of t, and we'll take the Fourier transform on both the sides. Here you are applying the time differentiation property, and time differentiation property gives that d by dt of x of t on differentiating in the time domain, we will have at the frequency domain as j omega into x of omega. That is your time differentiation property. Please refer to the property table. You can get it as d by dt of x of t will have the value of multiplying by j omega at the x of omega domain. That is, if you are taking the derivative at the time domain, it is equivalent to multiplying with j omega in the frequency domain. So first you have to find out the x of omega. That is, you can find out the x of omega of delta of t. We know that the x of omega or the Fourier transform of delta of t is nothing but 1. So 2 into delta of t will give you the value 2 into 1, which is equal to 2. Hence j omega into x of omega has got the value of 2, because d by dt of x of t is equal to j omega into x of omega. D by dt of x of t, on taking the Fourier transform, we will get 2 into Fourier transform of delta of t is 1, hence 2 into 1. Hence equating these two equations, we will have j omega into x of omega is equal to 2. From this you can get x of omega is nothing but 2 by j omega. Just take this j omega to the denominator section. Okay, that is the x of omega. Hence signum function has got the Fourier transform is equal to 2 by j omega. This is also another general conclusion. The same way you can plot the amplitude as well as the magnitude spectrum, amplitude as well as the phase spectrum, which is being mentioned in the previous cases, that is root of a square plus b square and tan inverse of b by a. Next we'll find out the Fourier transform of the unit step function, that is u of t. From the previous step, that is from the previous section, we have got it like the signum of t is 2 into u of t minus 1. Hence u of t can be also expressed in terms of signum of t. That is what is being done in the next section. That is signum of t is equal to 2 into u of t minus 1. Just rearrange the previous equation. Hence 2 into u of t is what? It is just 1 plus signum of t. And u of t is half plus half signum of t. That is your u of t. Now we'll take the Fourier transform on both the sides. U of t, you should take the Fourier transform, that is step by step we'll take. First we'll take the Fourier transform of half, then we'll take the Fourier transform of half into signum of t. For half, you have got the Fourier transform 2 pi into a into delta of omega A's value is 1 by 2. Hence, we'll have the Fourier transform of half as pi into delta of omega. And for half into signum of t, you know the signum of t has got the Fourier transform 2 by j omega. So on taking the Fourier transform 2 by j omega and multiplying with half, 2 and 2 gets cancelled. We'll get half signum of t as 1 by j omega. So just combine this equation 2 and equation 3, because equation 2 is the Fourier transform of half and equation 3 is the Fourier transform of half signum of t. Just combine these two. What you obtain is nothing but the Fourier transform of u of t, that is pi delta of omega plus 1 by j omega. In the similar fashion, we can say that the Fourier transform of u of minus t is equal to pi into delta of omega minus 1 by j omega. Just change this sign. Okay. And in this section, we are going to find out the Fourier transform of the function t into e raised to minus t into u of t. We'll take this section. It is of the form e raised to minus at into u of t, whose Fourier transform we have already found out, and that is equal to 1 by j omega plus a. In this case, the value of a is equal to 2. So, substituting a is equal to 2, we get e raised to minus 2t u of t has got the Fourier transform 1 by j omega plus 2. That is marked as equation number 1. By frequency differentiation property, we know t into x of t is j into d by d omega of x of omega. So, here we have already found out this x of omega. Next section is just the application of a frequency differentiation property. That is, here you have t into x of t form. So t into x of t will give you the x of omega in the form j into d by d omega of x of omega. X of omega is nothing but 1 by j omega plus 2. Hence, substituting here x of t is e raised to minus 2t u of t, and we have t into e raised to minus 2t u of t as the whole function. Applying frequency differentiation property, we have j into d by d omega of 1 by j omega plus 2. We know that this section, it is of the form d by dx of 1 by x, which is equal to minus 1 by x square. Hence, solving the RHS, we have j, which is the j here, d by d omega of 1 by j omega plus 2 as j into, we'll just differentiate that particular equation as minus 1 by j omega plus 2 whole square and just multiply by j. J into j is j square, which is equal to minus 1. Minus 1 minus 1 will become plus 1. Hence, the final answer is 1 by j omega plus 2 whole square. That is the RHS we have found out. The LHS is t into e raised to minus 2t u of t, for which you are finding out this section. And that section is nothing but 1 by j omega plus 2 whole square. Here, this can be also generalized. Here, if it is t into e raised to minus 2t u of t, the value is 1 by j omega plus 2 whole square. If it is t into e raised to minus at u of t, then it will be, instead of 2, it will be a. So, finally, we have listed almost all the important Fourier transform pairs. That is, for delta of t it is 1, u of t it is pi into delta of omega plus 1 by j omega, u of minus t it is pi into delta of omega minus 1 by j omega, delta of t minus t naught, that is the shifted impulse function, it is e raised to minus j omega t naught, and t into e raised to minus at u of t, which was just dealt now, it is 1 by a plus j omega square, e raised to at u of minus t, just change the sign. For 1 it is 2 pi into delta of omega, e raised to minus a mod t, double-sided exponential function, it is 2a by a square plus omega square. For cos omega naught, it is pi into delta of omega minus omega naught plus delta of omega plus omega naught. For sin omega naught, it is minus j pi into delta of omega minus omega naught minus delta of omega plus omega naught. And for 1 by a square plus t square, it is e raised to minus a mod omega. Signum of t, it is 2 by j omega. And this is the sine as well as the cosine functions with a phase shift. It is of the form minus j pi e raised to j phi delta of omega minus omega naught minus e raised to minus j phi delta of omega plus omega naught. And cos omega naught t plus phi is pi into e raised to j phi delta of omega minus omega naught plus e raised to minus j phi delta of omega plus omega naught. Okay. So that's all for the Ctft of the standard time functions. Hope you will find it useful. Thank you.